Okay, so it looks like I'm getting the go signal from up front. So I guess I should go. So this is the last installment of the parametricity course, and I'm just going to flip the slide for a minute to make sure that my thing is working. Yes, it is. Okay, good. So remember, of course, that the topic of this course is models of parametricity, or parametric polymorphism for system F. And what we're trying to do is extract the fibrational essence of Reynolds construction. And we've done most of the work for that now. But what we want to do is extract that vibrational essence, and then we want to use that to build not just a model of system F, like a more complicated model or a model where you can have an arbitrary base category, an arbitrary total category for a vibration, and some abstract notion of relations. What we really are trying to do is make a framework for making models, and then we can instantiate that framework in different ways to get different models for system F that have this nice parametricity property. Okay, so that's what we're going for, and we're on lecture 4 today. So that means we're finally going to use all of this infrastructure that we built up to make a model of system F, make our parametric model of system F. Okay. So, particularly, what we're going to do today is use the relations vibration on categories that we talked about last time. That's that vibration that's built by pullback. You're given a vibration U, and you make this vibration rel U. So this relations vibration. And we're going to insist that our relations vibration have enough structure that it can interpret arrow types, and it can interpret for all types, right? That's what we talked about last time. So we're going to insist on having the things that we set up last time right at the end. And you already know the punchline. The punchline is that we're going to interpret types as fibered functors, terms as fibered natural transformations. And this is how we're going to get our framework, our very general framework. So throughout the lecture today, I'm going to let rel U be not just any relations vibration, right, constructed from U, but I want it to be one of these equality-preserving arrow vibrations and a for-all vibration. In other words, I want it to have enough structure that it can interpret arrow types, and I want it to have enough structure that it can interpret for all types. Okay? Because we're going to interpret these things, so let's make sure we can do it. Okay. So let's try and build up the model. So I need to interpret types, and I need to interpret terms. So I'm going to start off with types, again, for 2 reasons. One is that types are easier, and secondly, types logically precede terms in system F, right? So I'm going to start with the types. So remember that we want the interpretation of every type to be a fibered functor from rel U to the cardinality of this context to rel U. So the reason I have a functor is because I can't just take the interpretation of a type to be a relation. You might think you could do that, but you can't, because after all, this type might have type variables. So I need to interpret the type variables as well, and that's what the type context is going to do here, right? So you have to give me a bunch of things that can interpret types, and then I can give you an interpretation of my type tau. And similarly for terms when we get there. Okay? So I'm going to define these fibered functors. I'm going to do it by induction on the types. So if you think in terms of making type index logical relations, I'm kind of making a logical relation, but I'm doing it in a categorical way. Okay? So when Amal starts talking about logical relations, she's talking about this kind of thing. So before I put that up, I should have asked you what we should do for type variables, because by now, we've done this a couple times by now, right? So I want to give, this is going to be a fibered functor, so it's got 2 pieces. It's got an object piece, and it's got a relational piece. So for the object piece, I have to give you a bunch of things that can be object interpretations of types. So that's stuff down in the base of my relations vibration. And how do I interpret a type variable? I just project out the correct thing from my context. And similarly, for the relational interpretation of a type variable, well, I have a whole context of relations, so I just project out the correct relation. So there's nothing new here. This is exactly what we saw before. And of course, if my relations are sort of pairwise over these interpretations of possible interpretations of types, then I'm going to want these two pieces to hang together in such a way that I get an abstraction theorem, and we will do that. We'll see that later when we start talking about terms. But right now, I have complete independence in the way that I interpret types at the object level, in this case type variables at the object level, and types, in this case type variables at the relation level. So this is exactly mirroring what we had when we were looking at the particular relations fibration rel over set, right? Rel over set cross set, I guess I should say. The relations fibration on set is exactly what we had before. Okay, so that's type variables. How about arrow types? Well, we've set up a bunch of infrastructure so that we can interpret arrow types using exponentials, or using this exponential arrow. Right, we have an equality-preserving arrow fibration. That means I have these exponential arrows. So I just want to interpret a type tau1, arrow tau2, as tau1, tau2. Well, actually, it's the interpretation of tau1, the interpretation of tau2, and I want to join them using this exponential arrow. This is exactly what we did when we looked at Reynolds stuff through a fibrational lens. The only difference is that this arrow was the arrow between sets. This one was, this big fat arrow now was the arrow between sets, because the function space arrow is the exponential in set. So I'm just generalizing to more general categories, but I'm basically doing the same thing. So this arrow is a syntactic arrow, and this arrow, this double arrow, is the exponential arrow, semantic arrow. Okay? Okay. So that's not too bad. But notice I've cheated a little bit, because here I gave two semantics. I gave an object semantics for variables, and I gave a relational semantics for variables, and you don't see any little zeros or R subscripts. And that's because I've just given the fibered functor sort of in one fell swoop, rather than by giving the pieces. Okay? So I could have said the object interpretation is this thing, but with little O's everywhere and a little O here. But I didn't do that. And similarly for the R's, right, for the relational interpretations. But I didn't. So I'm kind of abusing notation, because I'm thinking of this exponential as somehow the bundled up package of exponentials for both the base and the total category in my relations fibration. Okay, and I'm going to do that throughout. But here I had to give the pieces explicitly. Okay. And what about for all types? Well, remember, again, we're in an equality-preserving arrow fibration. That is also a for all fibration. So that means I have this for all thing. And I will remind you, when we go around and interpret our terms, I'm going to need to remind you about some properties of this arrow and this for all. But just like right now, I can say this exponential arrow exists in my category because I'm saying I have an equality-preserving arrow fibration, so that means it's an arrow fibration. So that means I've got this. In the same way, I'm assuming that my fibration is a for all fibration, so that means I've got this for all thing. So I'm going to interpret my for all types as for all. This is something that maps functors to functors. So the interpretation in delta comma alpha of tau is a fibered functor. And my for all is going to map that fibered functor to a new fibered functor. And that new fibered functor is the thing I'm going to take as my interpretation of for all alpha tau. But in a slightly smaller context, right? Okay. So for all, you might remember from last time, maps fibered functors to fibered functors. It does a little bit more. It actually maps equality-preserving fibered functors to equality-preserving fibered functors. But again, I'll remind you of that in a little bit more detail in just a minute. Okay, but I've played this same game where instead of giving the components, the O and R components, the object and relational components, I've just written the whole thing together, the whole interpretation together. Okay, so it looks like I've done the same thing for arrow types and for all types, but actually I just want to remind you that I've done something a little bit different in both those cases. I don't think it's obvious from the notation up here. So remember when we were talking about these equality-preserving arrow fibrations, we said the following. So I have to be careful because I have to hold that. Okay, here's what we said. We said you've got a Cartesian closed category in the base. You've got a Cartesian closed category on the total category, and the fibration preserves that Cartesian closed structure. So that's why I have an arrow here, this double arrow. I have this exponential arrow on the base. I have another one in the total category, and that's preserved. But remember that when we talked about these for all fibrations, I specifically said, well, you might think that you could play the same game. Let me have a for all down here on the base, let me have a for all up here on the total category, and let me have them be linked somehow by the fibration. And I said, that's exactly the wrong idea. Okay? So what we did instead is we said, well, let's have one for all that is composed of two for all somehow, but one for all that's actually has the right properties that we need. It looks like it's the same thing, but here we have two things that are linked up, and here we have one thing. Okay, and each one has two pieces, right? This has an exponential in the base and an exponential in the total category, and this one has a component of for all that's in the base and a component of for all that's in the total category, but they're constructed differently. Okay. Okay. So there is something kind of interesting happening here. Okay, and finally, I'll just remind you that as when we looked at the relations fibration on set, I don't need a definition of what the fibered functors are going to do on morphisms because the domains are discrete. Okay, right? I've got discrete rel U here, so I don't need to worry about morphisms. I've only got identity morphisms. Okay, so it's exactly the same thing as before. Yep. That's what I said. I mean, I do have them, but the only ones are the identity, so I don't need to worry about them, right? Because we know what functors do to those. But you're right. They're there. They're just not very interesting. There's enough stuff going on without them, right? Yeah, quite. Okay. Okay, so let's just look at our type interpretations. And I claim that they're equality preserving. And remember, this is exactly what we want in order to have the identity extension lemma, right? Remember, I showed you last time how saying that type interpretations are equality preserving is exactly the same thing as saying that we have the identity extension lemma. So let's just stand back and make sure we have that. Well, the interpretation of every system F type is an equality preserving fibered functor. That's a proposition. I'm not going to prove it here for you, but the proof is just an induction on the structure of tau. So you can prove it for yourself. I can't remember if it's in the exercises or not. But if it isn't, it should be. Okay. And then if I have a for all type, the key point is that if I have a for all type, like if tau is for all alpha tau prime, then remember that we interpret tau for all alpha tau prime as for all, we just saw this on the previous slide, as for all of the interpretation of tau prime, but in a slightly larger context. And the whole point here is that this interpretation of tau is equality preserving when the interpretation of tau prime is, just because we're assuming that we have this for all thing. So this for all thing takes equality preserving functors to equality preserving functors. So the whole definition of for all makes sure that equality preserving things go to equality preserving things. So if this piece is equality preserving, that's one of these guys, then because for all exists in my fibration, because I'm assuming I have an equality preserving arrow fibration, that's also a for all fibration, then I know that when I apply for all to it, I get something that's equality preserving. So that's how I handle the for all case of the induction. Okay? Yeah?
What does it mean for all to be naturally bound?
Yeah, it means that, so what's happening here is that I should have used cardinality of delta, so that's a really good question. What it means for all to be natural in n is that, see how there's this exponent n here? So here, it should be cardinality of delta should be n, okay? Because I've got a context, and I've got cardinality of delta, well, plus one things. So this fibered functor is going to go from rel u to the cardinality of delta plus 1 to rel u. And what I'm going to get is something over here that goes from rel u to the cardinality of delta to rel u. So I shouldn't have used n. It's just, for me, n is always a cardinality of delta. Does that make sense?
Yeah, but how is that related to natural?
Well, it needs to be natural in end. So the things have to hang together for different ends. They have to hang together nicely for different ends. So you can write out a naturality diagram, okay? And a naturality diagram with respect to n, and that will kind of show you that the interpretations are going to hang together nicely, okay? So it gives you, again, we're trying to get uniformity. Naturality is about uniformity. Okay. So again, the point is that the very existence of for all in our for all fibration guarantees the for all case of the induction. Okay, so what this tells us, remember when we looked at Reynolds' model, what we did was we gave the interpretation for types, and then afterward we said, okay, so we can prove that we have the identity extension lemma, or we can prove afterward, post facto, we can prove afterward that the interpretations of types preserve equality. Well, here, because we've assumed that we have an equality-preserving aerofibration that is a for-all fibration, we're actually kind of baking in the equality preservation into our model. Okay? So when we looked at Reynolds' model through the vibrational lens of this relations vibration last time, we just picked this vibration because it was reminiscent of his original construction. It models that exactly. And then we kind of looked at what happened there and gave our interpretations of types and also of terms. We gave our interpretation of types. And then afterward, we had to go through and say, okay, well, now let's see, do we have this identity extension property? But here, we kind of front load the work. We kind of have to do the work up front because we have to know that we have a for-all fibration, equality-preserving aerofibration, that's also a for-all fibration up front. So you have to do the work when you construct the model, not when you're interpreting the terms and the types. Okay, so that's a difference between the two. You have to do the work somewhere. It's just a question of where you do the work. And in Reynolds' setting or in the relations vibration setting, you can just, look at, you don't have to kind of, you don't a priori show that you have a for-all fibration, although you do, obviously. But you just sort of start defining your interpretations, and then afterwards you say, oh yeah, okay, good, I've got all the structure I need. But here we assume we have the structure we need, and then we show that that's enough to interpret our types and terms. Okay. But it's just a question of moving the work around a little bit. Okay, in the case when your original fibration, the U here, from which you constructed your relations vibration, has some nice properties, then you can infer this for all fibration requirement. Okay, so there are some papers that I'll reference at the end, and they talk a little bit more about how you can get this for all fibration requirement. Not important for us so much. Okay, so that's what's going on with the types. So questions about that? So we just assumed that we had a bunch of structure that we needed to interpret the types, and then we interpreted the types, and it was not too hard. But of course, if you want to apply this construction and you have a particular model in mind, you have to do all that work up front to show that you have that the kind of model that you have in mind has all the right properties, right? Okay. What about terms? Well, let me just remind you that in a Cartesian closed category, not only do you have products and exponentials, and we need Cartesian closed categories, right? Because we need products to interpret the context, and we need exponentials, as you just saw, to interpret the arrow types. But they have this relation, right? They have this nice relationship that if I have a morphism between W cross X and Y, then I have a corresponding morphism between W and the exponential object X cross Y. Okay, so it isn't just that I have X and I have products and I have exponentials, it's that they have this relationship between them. Okay, and we call, I'm going to use lambda to represent that morphism. So I think things are going to get a little tricky here with the hands and the mic. So remember when Ed introduced exponentials, W cross X. So he probably drew something like this. And he said the point of an exponential is that if you have a morphism like that, then, which way did I do it? Then I have a corresponding morphism from w to the exponential of x and y. And if this morphism here was called g, then this one is called lambda g. Yeah, I think I need x here. Okay. And here I need the identity. It's like the identity is not going to work there. Okay, but now I think I'm good. Right, so this one is called g, and he called this one lambda g. And then he said something like, notice how clever I was that I called this lambda. Right, because he wanted to be suggestive. Well, that's what I'm calling this one lambda too, because, of course, that's what we're going to use to interpret our lambda terms. Okay, and then this map, I think he might have called it eval or something like eval. Oh, he called it epsilon, okay. Well, I'm not going to call it epsilon, I'm going to call it eval, but I'm going to write it as EV. But it's the same map. And the whole point is that the exponential makes the diagram commute, and it's the best thing that does that, right? Okay, so that's the lambda I mean. And I think he might also have mentioned that you can think of lambda as uncurrying. Right? Okay, if you're being a functional programmer today. Okay, so we have this nice, it isn't just that we have exponential objects and we have products, it's that we have this nice relationship between them. And here's eval. And just as in the picture over here, it goes from x arrow y, from this exponential object cross x into y. So it's exactly the thing I drew on the board. Okay, so try to remember that. And so I've got this isomorphism called lambda. And I also, because I'm in a for all fibration, I have this other isomorphism called phi sub n. Well, it's like a family. And what does it do? Well, remember that there's a relationship between projection and for all. And the relationship can be captured in this isomorphism. So just like the relationship between times and exponents can be captured by the isomorphism lambda, the relationship between projection onto the first n components and for all on n variables can be captured by this isomorphism. Okay? So it's exactly analogous. I'm going to call this phi sub n, and I'm going to use this to interpret my type abstraction terms, big lambda terms. Okay, so let's see how this goes. Term variables. So I tried to actually here get rid of the m's and the n's, but in case I didn't, let me just say that I always think of the cardinality of delta as being n, so n type variables and m term variables, right? So delta is the type context for my term, and m is a term context for my term. So I've got n type variables and m term variables, but I think I actually got rid of the m and n here. Okay, so I want to interpret every term as a fibered natural transformation, and just as in Reynolds models, I want it to be a natural transformation between the interpretation of the term context and the interpretation of the type. Okay, so just like before. So I'm just going to try and go through, I won't go through really quickly, but I'm not going to go through in excruciating detail, because I think with a lot of this stuff, there's a lot of notation, right? It's pretty notation heavy. And I think ultimately you just kind of have to sit down in the privacy of your own head and unpack it. But I'll try to walk you through it a little bit so that if you decide you want to do that, you have the signposts available to you. Okay? So that's how you can use the slides. Okay, so suppose I have a variable, right, that my term is a term variable. Then that means it must have been in my term context. So what am I going to do to interpret that term variable? Well, it should go from the interpretation of gamma, should be some natural transformation that goes from the interpretation of gamma to the interpretation of tau, and all I'm going to do is just project out the right piece. Exactly what we did before. Okay? And of course, I'm only giving my interpretation once, but I've really got an object interpretation and a relation interpretation here. So I'm using pi sub I both at the object level and at the relation level. So I'm kind of identifying a lot of different things. Okay, so that's term variables. Is that okay? Okay. And this specializes to our set interpretation of variables. So we actually get back what we had before in the specific example of the relations vibration on set. What about term abstractions? So if I have a term with a little lambda, so lambda x dot t, and it's of type tau 1 arrow tau 2, I have to tell you how to interpret this. Well, it should be something that goes from the context to the return type. Well, the interpretation of the context to the interpretation of the return type. Well, the interpretation of the return type is the interpretation of tau 1 arrow tau 2, and that's just the interpretation of tau 1 exponential, the interpretation of tau 2, right, using the stuff we did on the last slide. So I'm going to define my interpretation of lambda x dot t to be lambda of the interpretation of t, but in a slightly larger context. So this is the same lambda. That lambda is that lambda. Okay? So let's see why that's sensible. Okay. So in order to form lambda x dot t, I had to have had that in a slightly larger context I could form t, right? So the induction hypothesis gives me that the interpretation in that larger context of t must go from its context, from the interpretation of its context, which is just the product of the interpretation of gamma and the interpretation of tau 1, to the interpretation of tau 2. Okay? And because lambda is that lambda, it's the right adjoint to product in both B and E, then that means that I can apply lambda to something that looks like this, right? And I get something that has an exponential in it. So if I apply lambda to something of this type, I exactly get something that has the same context, and now I have the exponential between, whatever was the last component and the thing that was the return type. Okay? So my lambda is like tailor-made to interpret my lambda terms. Okay? And again, if you look at this construction in the specific example of the relations vibration on set, you get exactly what we had before. So it really is a generalization. I keep saying we're making a generalization, but we really are making a generalization. Okay, so anything about that? Is that okay? So my lambda is just set up to do exactly the right thing. What about term applications? This is a little bit harder to read, but it's not too bad. So I'm using this eval here on the board. That's the same as this eval. Okay, so what's happening? I want to interpret an application of T2 to T1. So I should go from the context in which I'm doing that interpretation to the return type, which would be T2. So I'm going to define it to be this crazy thing, and I have to unpack that a little bit, but it's not hard. It's exactly what you think it is, probably. All right, so let's dig down and see what's going on. If I look at the judgment for T1, I know that the interpretation of T1 goes from the context in which I'm doing in which I'm forming T1 to the interpretation of its return type. That's just one induction hypothesis. Here's the second one. So for that one, I have the same kind of property. It's just that, remember, on the right-hand side here, the return type is an arrow type, and I interpret arrow types as exponentials. Okay? So if I were to pair up those two terms, then I have to tell you what that pairing thing is. So the pairing thing is going to do this. If you give me something that takes a bunch of inputs and gives me a y, and something that takes the same bunch of inputs and gives me a w, then if you give me that same bunch of inputs, I'm just going to split it and apply each of these two functions to it, and I'll get a pair of results y cross w. Okay? So here's the definition. Right, I take the input, I split it, and apply each of the input functions to it. So that's what I'm using right here. So what's happening? So if I look at this piece, if I were to apply this to a bunch of x's, a bunch of things that could interpret my type variables, I'd get something here. I'd get something just of type interpretation of tau 1. If I did the same, applied this term interpretation to exactly the same context, I'd get something that looks like this. Okay, so suppressing the deltas, what I've just said is if I look at this pair of interpretations, then I should give one context and I should get something of the return type of the first thing and the return type of the second thing. And that's exactly the kind of thing that eval can apply to, right? Because what kinds of things can eval apply to? Well, I have to have an exponential between x and y and an x, and I should get a y. And that's exactly what I've got here. I've got tau 1, the exponential of tau 1 and tau 2, and a tau 1, so I should get a tau 2. And that's what I'm looking for. So again, it's these properties of the exponential that are exactly perfect for interpreting my type abstractions and my type applications. Again, if you specialize to set, you'll get exactly what we had before in the specific example of the relations vibration on set. Okay. So I only have term abstractions and term applications type abstractions and type applications to do. But of course, that's where we had ran into trouble. So it seems like things are going to get really complicated from here, but they're not going to, because we've already built into our models the things that we need. So let's have a look at type abstraction. So here, if I'm trying to look at lambda alpha dot tau and trying to interpret it, then as always, I should go from the interpretation of its context to the interpretation of its return type. But remember that the interpretation of this type is just the for all outside. This is the semantic for all with the applied to the interpretation of tau in a slightly larger context, right? That's how we defined our interpretations. Okay. So I'm going to make this definition. I'm going to define the interpretation of for all alpha tau, t, to be the interpretation of t. Well, this phi was, let's see if I can go back. That was the thing that was playing the role of lambda, but for the for all types. So let me just go back and remind you. We did a lot of this then. I think we were, whoops, here. Okay, so it's the thing that goes from the projection. So it codes up the relationship between projection and for all, just like lambda coded up the projection between products and arrow types, or exponentials, I should say. Okay. So here we were. So here, I want to look at this interpretation of t in a slightly larger context. And I want to apply my phi to it. Okay? So why is that sensible? Well, let's have a look at what we get from the induction hypothesis. We get, from the induction hypothesis, we get that the interpretation of t in a slightly larger context should be a natural transformation from the interpretation of that slightly larger context to the return type of the judgment, so the return type of t. But remember that in order to have this term be well-formed, I have to know that alpha is not free in gamma. If you go back and just look at the rules for system F, this has nothing to do with vibrational anything. Just the rules for system F. In order to form this term, I have to know that alpha isn't appearing free in gamma. Okay, so let's just unpack the interpretation of gamma in this context, delta comma alpha. Well, this should take cardinality of delta plus 1 things that can interpret types, right? But I don't need them all because alpha isn't appearing in gamma. So if I just threw away that last one, I could still interpret gamma. So that's what the pi sub gamma does. It keeps the first gamma many, cardinality of gamma many. Okay? So this interpretation of gamma in the slightly larger context where you give cardinality of delta plus 1 possible type interpretations is the same as give me those cardinality of delta plus 1 type interpretations. I think that should be a delta. And I'll throw away the last one. I'll interpret gamma in that context, and that'll give me the same thing. Okay, so I didn't do anything to the return type here, but I did change the representation of the domain type. Okay, so that's fine. But now remember that this is exactly the kind of thing I can apply my phi to, because phi would take something that looked like this, and it would give me something from the thing I'm precomposing with projection, so that's this, and just interpretation of gamma. And I should go to for all of the thing that used to be in the codomain. And that's exactly the right kind of thing, at least. Okay, so that's my sanity check. That's what we've been doing as we go along, just doing a sanity check. So I think things are looking pretty good. I can't say that if you specialize this, you get exactly what we got in the relations vibration, because, well, at least when we were looking at Reynolds construction, we had to stop because this construction didn't quite work. But this is a reasonable generalization of that. How about type applications? It's the same thing, only I'm going to use my phi inverse rather than phi. So what happens? Well, I look at the interpretation of my type application. I should go from the interpretation of the context to the interpretation of the return type. And I'm going to make this definition. It's not as bad as it looks because you already know what all the pieces are. Okay, so why is this sensible? The induction hypothesis gives me an interpretation of for all alpha tau 2, right? Otherwise, I wouldn't be able to form the application of t to tau 1. So what about it? Well, I know that its interpretation goes from the interpretation of its context to the interpretation of the return type. And I know that the interpretation of this return type is just my for all applied to the interpretation of the body of the for all type, but in a slightly larger context. Oops. Okay, so what do I do? Well, the first thing, so this whole business here is going to expect, that should also be delta. I guess I got really excited about gamma, but all those cardinality gamma should be cardinality deltas. I'll change them after the lecture's over. Okay, so what do? I give cardinality of delta many interpretations of types, and what do I do with them? What I'm going to do is split. Remember these arrows here, these brackets split. So I'm going to take a context. I'm just going to duplicate the first bunch of them, and I'm going to have one more for interpreting this, this type alpha. Okay, so I just keep however many I had, just duplicate them, don't do anything exciting. Here I interpret tau 1 with respect to them. Okay, so now I've got a context that's a little bit bigger, and in that slightly larger context, I can look at the interpretation of my for all type, but I want to look at phi inverse of it. Why do I want to look at phi inverse of it? Well, because if I look at the thing that of the interpretation of the term that has the for all type, it goes, as we just said, from the interpretation of its context to the interpretation of the return type. And phi inverse, remember, was a thing that took maps that go from here to here to ones that go from projection, this composed with projection, to the follow-on type. And that's exactly what we need here in order to make this thing be sensible. Now, we have to do a bit more work because I've got this return type and it's got some substitutions, and I don't see anything of any substitutions anywhere down here. So it isn't obviously correct, but you have to prove a little substitution lemma that says that you end up with something that has the right type. Okay, I'm not going to do that because it's just a bunch of munging around with syntax and definitions and unfolding definitions. But you do have to do a little bit more work, but it does work out. Okay, so using, so let's just stop there. Okay, so using all of this infrastructure that we set up, we can interpret types, so variable types, arrow types, and for all types. And we can interpret terms, by which I mean variable terms, also type abstractions, type applications, but term abstractions and term applications. Okay. Type abstractions, type applications, we interpret using the for all and this phi that goes with it. Type abstractions, type applications, term abstractions, term applications, we interpret using exponentials and the lambda that goes with it. Okay. So we made sure that we had enough stuff to interpret our terms and our types. And now what we'd really like is for everything to hang together nicely. Because in a way, I haven't said very much, except for with the for all types, I haven't said anything that is specific to any fibrational setting. A lot of this stuff you can just do in an arbitrary Cartesian closed category. Okay? But of course, I don't want to do that because I want my interpretations to hang together nicely so I get my nice parametricity property. Okay. But I've got the interpretation of types, I've got my interpretation of terms, so everything's looking pretty good. The only thing is that, of course, I don't just want to interpret types and terms. I have a whole equational theory I'm trying to model, right? I mean, I have beta reduction and eta reduction and alpha equivalence and all kinds of computational properties, and I want to model those. So you have to prove some stuff, okay? So hopefully I convince you that the model is sensible by construction. Because we can see Reynolds' model through the fibrational lens as being something about the relations vibration on set, we can see Reynolds' model as an instance of this framework that we've just constructed, assuming if we have a constructive meta theory, okay? But you still have to prove that your equational theory is validated. So I'd still have to prove that, if I interpret a type application and actually perform the type application, I end up with the same interpretations. And similarly for type abstractions with respect to eta equivalence. And I'd have to prove the same thing for term applications, right? If I interpret a term application and then I actually perform it, I should still end up with, I shouldn't change my interpretation. And similarly for term abstraction with respect to eta equivalence. So I have a bunch of things I have to check, a bunch of properties I have to check to make sure that I'm actually modeling the equational theory that I'm interested in and not just, well, I gave some interpretations for types and terms. Do they respect the equational theory? Oh, I don't care. So I don't quite want that, right? Okay. So there's still work to do. But again, these are tend to be by induction on the structure of types and terms. Okay. But if you don't want to do all of that, you can do something slightly different. You can do the work in a different way. So you can prove that the model that I just defined actually gives you what's called a lambda 2 fibration, and I know I mentioned those last time. And the reason that would suffice is because Seeley showed that you can always interpret system F soundly. In other words, by in such a way that you respect the computational properties. In a lambda 2 fibration. So this would be another way to slice the work. You still have to do the work. You still have to know that your model or your model framework is working properly. So you have to do a little bit of follow-up, but you can do it. And then the theorem that we get is that, well, all the stuff I just gave you gives a lambda 2 fibration. So I can, if I have an equality-preserving arrow fibration, that's also a lambda fibration, then I can make a lambda 2 fibration where I interpret my types as equality-preserving fibered functors and my terms as fibered natural transformations. So that's what we've been working toward. Okay. So do you remember, you might not remember this picture, but we had a picture that looked a lot like this when we looked at the relations fibration on set. It's the same picture. Right, it was really easy to make once we made the other one, right? Because all I did was instead of rel, I put rel E. Instead of set, I put B. And I suppressed all the deltas, right, all the type contexts everywhere. But this is exactly the same picture we had before. But now it's in this much more general setting. Okay? So that's why I say that what we've got is like a framework, not just the one model for the relations fibration on set, but we've actually got this, this kind of framework that will tell you how to make a model anytime you have a fibration that satisfies the properties that you want. Okay, if we unwind the theorem that we just had, or unwind the picture, right? Oops, if we unwind this picture, then what we see is we have an object interpretation of types as fibered functors on the base, and a relational interpretation of types as as functor on the base. A relational interpretation of types as a functor on the total category, and that those two interpretations form a fibered functor. And we also have the identity extension lemma in the form of showing that that fibered functor is equality preserving. The fibered functor that interprets types is, those things are all equality preserving. We have an object interpretation of terms as fibered natural transformations between their context and their return types. And one way to say it is to say we also have an abstraction theorem. But another way to say that is to say we also have a relational interpretation of terms as natural transformations between their contexts and their return types, and that the relational interpretation of the term and the relational interpretation and the object interpretation of the term give you a fibered natural transformation. Okay, so saying that we have the abstraction theorem is the same thing as saying we've got this extra structure here in the form of a relational interpretation for terms. And that was something that Reynolds didn't have. I mean, he had it, but he didn't say it that way, right? Okay, so that's all this slide says. So what do we have? Object interpretation of types, relational interpretation of types, identity extension lemma in the form of equality preservingness, object interpretation of terms, abstraction theorem, which is really the same thing as saying we have a relational interpretation of terms as well. Okay, so in addition to that, I keep mentioning these kind of litmus test properties that you can apply to your model to make sure you've got a good model. Because we've made a lambda 2 fibration, we have a tool for showing those. We have an internal language for our model, and we can use it to show that we have those properties. So again, those properties are things like functors that should have initial algebras do. So that means you can model algebraic data types, if you're interested in those. Functors that should have final coalgebras do. That means that you can model co-inductive data types. Parametricity implies dinaturality, another property that, that you want good models to have. Okay, so you can, and there are other things too, but these are the main ones. So you can check that you have a good model. Okay, so I have this summing up slide, except that then I have a couple more slides. but let's just have the summing up slide. Well, you already know the summing up, right? Because I told you that if you never ever heard the word fibration, you could build a model of system F and you would say, okay, I can interpret my types as functors, I can interpret my terms as natural transformations. And all I really want to do here is put fibered everywhere. Okay, and so that's the punchline. If you take one thing away, that's the thing that you can take away. So here we're just, if you want to talk about parametricity, just make everything fibered. And as I said in the beginning, part of the reason, there are many, many other models, also not only of system F, but parametric models of system F, or models that verify parametricity. But I like this one because I think it hits kind of a sweet spot between the simplicity of functorial models where you interpret types as functors, and the ability to prove those litmus test properties. So it might look like it's heavy, and it's heavy for 4 days, to be sure. But, well, you should see some of the other models. That's all I will say, okay? So you think this was bad? Well, but this I think you can get your head around. I mean, you can get the idea. Well, I don't know. Maybe you should tell me. Do you think you got the idea? Because, I mean, I see people kind of nodding along. Other people are, doing whatever they're doing. But some people are kind of nodding, yeah, okay. And so even if you don't get all the details, I hope you have the sense that you could dig down and make the details work, right? But the idea is pretty simple. I could have just walked in here and said, oh, just say fibered everywhere. Now we're done. Now you've got like 3.5 free hours. Okay, but I didn't do it that way. All right, so here are my extra slides. That was the summing up slide with the post-summing up slides. A little bit weird, but well, I keep saying I made this framework, not just a model. So you might be thinking, okay, what kinds of examples do we have? And as I said, you have to do all the, you kind of have to front load the work for making examples, because if you want to interpret system F like in a per model, in a realizability model or something, you have to show that your model has all the properties that you need in order to use this framework, right? So you have to front load all that work before, but once you do that, then you get all this stuff for free. For free, modulo all the pain that you already went through. Okay, so many well-known models are instances of our framework. I think I've mentioned that before. But sometimes you have to regard them as being, for example, internal to the calculus of constructions with a predicative set. So you have to work in a constructive meta theory. Or at least one of the examples that we have in the paper has to be regarded as internal to the category of omega sets. So you have to work kind of constructively, right? That was the whole thing about that's the whole thing about Reynolds' original construction not really working. So these are in the MFPS paper, the one that's linked off of my site. And you can look at it there. And some of these things are discussed in the exercises for today and other days. In particular, I ask you to show that if you look at the identity fibration from set to set, you get an instance of our framework, but it models ad hoc polymorphism, not a parametric polymorphism. And that's because it doesn't have, you get a fibration, but this isn't a relation fibration. So it doesn't satisfy that aspect. But you'd get a fibration that is somehow an instance of this, but doesn't quite do the right thing. And I also ask you to show that if you ignore size issues, then Reynolds construction gives you an instance of this framework if you think about the relations fibration on set. Finally, there's this really famous model, this PER model, and again, that's also an instance. But you have to, as I said, you have to understand the bifibrations as somehow being internal to some category. And okay, so it's complicated, but you can do it. There are also realizability models. There's a hand being raised silently. Can you say that again? Oh, what does it mean to say delicate? Yeah, all I mean by delicate is that you have to front load all that work, right? Yeah. And it can be non-trivial. Yeah. Okay, so the last thing to say is that it's true that there are known models and of system F, parametric models, and I've just mentioned how several of them, many of them can be seen as instances of this framework. So that makes it sound like this framework is only descriptive. It's only talking about known models and showing you like a uniform way to think about them. But that's not really true. It's also prescriptive. So in other words, I can use this framework to construct models that I didn't already know about. Okay? So how do you do that? So you've got your fibration, and you've got your base category and your total category and your functor between them. If you change the base fibration, you're changing your object interpretations of system F. So you're saying, all right, I want to interpret, I want to interpret system F in a realizability model, in a PER model, in something other than set-like things, or even just some Cartesian closed category. Okay. Up here, you've got your total category, and remember, that's like your predicates on your base. So this is sort of, and from that, you make this relations fibration. So a relation is like a predicate on a binary predicate, right? So what you're really, if you change the total category, then and the functor, then you're sort of changing your notion of relation. So you can say, I want to change the way I interpret my interpret system F, and you can say, I want to change my notion of relatedness. And that's where the power comes from, right? Because you can talk about all these things simultaneously. Okay, so changing the base category changes the object model. Changing the total category and the fibration changes the notion of relational logic you're going to use. And if you use non-standard relations, so if you are clever in how you choose your total category, your notion of relation, then, for example, you could make a model of multi-valued parametricity over some crazy structure. Okay, so you can make new models. So it's a model that wasn't known before. So you can make new models too, just by looking for instances of the framework. I thought I might mention some extensions. The way I've showed you the way I've developed this framework here, it bakes the identity extension limit into our framework just by looking at that for all, and the way that it takes equality-preserving things to equality-preserving things. But I think I said on that slide that you can actually derive the for all and its properties from more primitive assumptions. So there's a Wallach paper that does that. There's, if you make rel u from u, then you want rel u always to be an equality-preserving arrow fibration. I just assumed it here. But you might say, I'm making rel u from u, so are there properties of u that will ensure that rel u is an equality-preserving arrow fibration? And the answer is yes. And there's a paper that explores that there. And yes, a theory paper did get the best paper award at ETAPS. So it wasn't my paper, but still, it's nice. Hooray. At Wadlerfest, some random collection of people who work on this stuff, also developed a proof-relevant version of our framework. So ours is proof-irrelevant, right? Okay. Because it just says either things are related or they're not related. It doesn't say things are related this way or things are related this way or have this witness and that witness and another witness. Okay. And some other collection of people who work on this kind of stuff are trying to incorporate computational effects into this framework so that then you could talk about polymorphic lambda calculi with computational effects. So that would be nice. And I didn't put it up here, but another person, so this is one of the postdocs I have right now, and the other postdoc I have right now is trying to look at connections between this framework and homotopy type theory. So there's a lot of active work right now in this area, so many, many more. So, well, maybe there's even more than I know about. Okay, I always leave you with some references. So here are some references. These are some other papers that you can read that are on this topic. There are way more than the ones I've shown you over the 4 lectures, but there are a lot of really, you could spend many, many happy hours, right, with your face in here. Okay, so I think that's it.
I want rel U to be a quality preserving error.
Rel U.
Yeah, so not U, but rel U.
Okay. Now, how does that guarantee that the category where your objects are polypreserving fiber functors and
see, it's not easy, is it?
Yeah, the morphisms are fiber data transformations. How does that guarantee the existence of this?
Okay, so you have to, so that's a really good question. So I'm going to try and summarize that in case everybody didn't hear me. So, okay, so yeah, you've got some exponentials in your original original base category, in your original total category, and you know that your functor preserves those. But how does that tell you that when you pass to the relations vibration, you still have exponentials?
Yeah.
That's it, right?
I guess we're constructing totally different categories.
Yeah, you are. But pullbacks preserve a lot of these things. They preserve a lot of constructions that you want. And in this case, it's because you're constructing the relations vibration that pullback. Okay.
How to work it out.
Yeah, I didn't say that. You're right, I didn't say it. But you're too fast. You're paying too much attention. You're right.
I had a second question.
Do you remember what it was?
No.
Should we let somebody else ask a question and maybe it'll come back?
Oh, yeah, sure.
And, oh, maybe there are no questions. Does anybody else have a question? Yes? Yeah. So I talked to offline. Is that okay? Okay.
Yeah, I have another.
Okay, you thought of it. Okay.
So you said the original construction breakup is completely captured by the coding evaluation from set errors using this It's just
not
instance.
set of the predicate vibration.
Oh, I got it wrong. So what is it?
The predicate vibration. I didn't talk about it. So here's what we did. We looked at Reynolds' construction on Friday, and then we tried to look at it yesterday through a vibrational lens. And so I just said, okay, you have this relations vibration on set. And then I said, okay, well, let's just notice that that is constructed by pullback, and then we'll generalize. Okay. But I didn't tell you what it's constructed from. So again, I think you're paying too much attention because you found all my omissions. So I didn't tell you what it's constructed from. It's constructed from something called a predicate vibration on set. And I could have said, here's a predicate vibration on set. I'm going to look at this, this pullback and make the relations vibration on set and so on and so forth in that way. But it just seemed like there was no point in 4 days to introduce yet another vibration.
So it's not true that REL, the relations vibration, REL over set is the pullback of the error.
No, it's not the code of vibration.
Okay.
It's object vibration.
Yeah, because I tried to work it out yesterday.
And you couldn't do it, right? Yeah. Yeah, I'm not surprised. Yeah, it didn't work. Sure. Okay, anything else? All right, well, thank you for letting me tell you about some things I think are really great. What's that?
So, as Luke said, I think this is the most complex course we've had so far at OPLSS. And while it's not easy to be an audience member, it's probably a lot harder to present this material. So, on behalf of everyone, Patricia, I'd like to thank you for decompressing the richness of this complex topic, and also for providing such a good source of fiber.